Alright, here's the instrument, the ESR-2501 version C ESR meter. This is the most recent version of a product that's been around for a while, often in the A or B revisions, and those are most noticeable by a different color case, and also that the versions earlier than version C only have a single button, whereas version C has two push buttons. This still photo shows what comes in the package. You get the actual ESR meter, that's in the lower right. You get a charging cable, which is a USB type A connector at one end, and a barrel connector at the other end, which plugs into the tester or the meter. You do not get the AC charger or power supply, which the cable plugs into at the opposite end. You need to provide that yourself, and this video will address that to some detail. Part of the tester or meter is the gray cable that you see coming out of it at the right end. That's the test lead cable, and just out of the frame at the bottom of the picture is where the cable splits into a red and black test lead, and these terminate with banana plugs, which are here shown plugged into red and black alligator clips, and those are for clipping onto the leads of a capacitor. You can also unplug the test leads from the alligator clips and plug them into the test probes, which are shown at left, also in red and black, and thereby use it to probe components that are mounted on circuit boards. If you're working in an area where you have adjacent components that you don't want to accidentally contact with the points of the test probes, then there are these black and red caps that snap over them and only leave exposed the very tips of the probes to make contact with the circuit board or a component. And that'll be useful for even things like surface mount parts. The probes themselves do not come with the test points in them. Instead, you get a set of 8 metal test points for the probes, which just screw into the probes. There are 4 of them in what the manufacturer just calls silver, and 4 more in what they call gold, and they do have those colors, although I doubt they're actually made of silver and gold. I'm not clear why you would use one over the other. Although some more of this will be shown in the actual video part instead of this narrated slideshow that starts the overall video, I still want to go over a few of these here because I can talk a little bit more about things that I didn't shoot as video. So this is the meter case opened up. There are 4 screws accessible from the back, and they use a Phillips screwdriver. You take those screws out, the front cover comes off and exposes the main circuit board with the LCD module plugged in and the black battery holder at the lower left of the image. There are also, you can see the 2 push buttons on the circuit board with plunger extensions coming up where they touch the back of the 2 buttons on the front of the case. Here's a close-up of the circuit board showing the battery holder in particular, and you can see we're on the circuit board right below the battery holder. It tells you with the silk screened text exactly which model and type of battery is required, so you don't have to go find documentation elsewhere. It's good that they put that on there. Here's another view of the same thing. You can see that there's underneath the LCD module, you can see that there's a multi-pin IC down there. Well, not multi-pin, but a larger IC. And that, I believe, is the microcontroller that runs the meter. So that would be what has the program in it. That's what would control the LCD. That's what would coordinate the activities of the other circuitry on the main circuit board. And I'll show another view of that. And here's that other view. You can see where the LCD module plugs in at the left side of the board, and then there's the microcontroller in a socket underneath the LCD module. There's a blue potentiometer there, which I didn't check when I had this thing open, but I believe that's going to be a contrast control for the LCD. So if you find that yours has issues with the contrast on the LCD image, you might pop it open and take a look at that blue trim pod and see if that's what that does, because its proximity to the LCD suggests that it's the contrast control potentiometer. Here's a view of the back of the circuit board, and you can see various components on there. Right on the left side is what's probably a 3-terminal voltage regulator of some sort. I didn't scope it out to see exactly what kind. And towards the center bottom of the circuit board in this view is a small transformer, which is probably used for voltage step up or step down. One of the ICs next to it is probably a controller for that. And then there are several ICs there, and I suspect that there's probably going to be some analog switches in there, maybe a couple op amps, some transistors, and things like that for controlling the analog section. That would be necessary for doing a lot of the measurement front-end circuitry. And here's the last of the still images. This just shows after I've installed the battery, and the battery does not come with the meter when you buy it from any of the suppliers I've seen. I guess they're keeping the price lower that way because the thing usually sells for in the high 30s or $40, and if they included the cost of the battery and the AC wall adapter for charging the battery, it would add at least another $10 to the price, so they put that off on the user. But in fact, AC wall wart power supplies are a dime a dozen these days, and a lot of people have them laying around from old mobile phones and such, so that makes sense. It would be nice if they at least gave you the option of buying the battery with the thing, but even then they're maybe in the range of $6 to $7 if you just buy them on Amazon or whatever. I've removed the screws, 4 screws on the back of the case, to take the cover off, and this is necessary to install the rechargeable battery. This is the type of battery. It's a lithium battery, type 14500. It's a 1600 milliampere hour battery, 3.7 volts. And these are readily available for just a few dollars on Amazon. They go to pains to point out that this unit does not come with a battery installed. You have to buy your own. I purchased 2, and one is already snapped into the holder inside the unit. Over on the left side is an LED with a hole for the power adapter. It does not come with a power adapter, and since there's no way to charge the battery internally unless you use a power adapter, you're going to need one. Now in my case, I've used this leftover cell phone charger, USB cell phone charger. And the tester does come with a short USB cable. At least it's a USB-A on one end. And then the other end has a small barrel connector, which does plug in here. Here's the included cable plugged into my cell phone charger, which again is just a 5-volt USB power supply. Usually these things put their specifications on them, but this one does not have it. Well, I'm sorry, it does too. It's on the side. It's calling itself a travel charger. This one's 100 volt to 240 volt universal, 50-60 hertz. Output is 5 volts. And it's up to 1 amp, which should be more than this needs to charge. With the charger plugged in, the LED is red. The instructions I've been able to put together from various sources state that the LED is red when charging and green after charging is complete. Charge time is estimated to be between 2 and 3 hours for a empty battery and less for a partially full battery. So I'm going to let this charge up. I should note that I tried operating this tester without a battery installed using the same charger, and while the LCD display would turn on as far as the backlighting goes, I wouldn't get anything on the display, so I'm assuming that it detects if it doesn't have a battery, or perhaps the adapter is only set up to trickle charge the battery and cannot provide enough power to really run the whole unit, or perhaps it actually monitors the power coming in here, or I'm sorry, the power on the battery itself and not the power coming in here, and refuses to turn on unless there's power in the battery. I'm going to give this time to charge up thoroughly and then see if it operates. This is a partially defective unit, since I think this cable fits very tightly into the hole, and some careless person at the factory, tugging the cable through the hole, manages to strip off a little bit of the insulation. That's not too good. But while it's doing this, I'm going to point out that unlike some other testers of this sort, which may only have like tweezers type test clips and therefore only work with in-circuit components and with a certain lead spacing, this one's more flexible, which is why I selected it. The test cable has banana plugs on the end, and then it comes with a pair of test probes, which the tips can be unscrewed, and several different types of tips and spares are included, as well as tips that cover up except for the very end, like that, so the rest of the probe isn't exposed. This is useful if you're working in very tight areas where the length of metal on the probe might short something else out. And then you can also put on a set of alligator clips which plug into the end of the cables here. So you can do it that way as well. Okay, the LED has turned green after a couple of hours. So I'm going to unplug the power adapter and the LED goes out. Alright, well, I originally started out this video to be an exploration where I just stumbled my way through it and experimented, and this was because I couldn't find any user manual for the product. Just a few snippets of things I'd found online. Various sellers of this would have some brief statement in their sales listing that might give some clues about various aspects of it, but some of those were wrong, some of those were right. Anyway, as I was editing the video with all my explorations, even trimming out a lot of the fat, it was getting to be a really long video, so I decided to change my tactic on it and reshoot just based on the things that I'd already learned. So I'll start out this portion with the meter, and it's charged, and I'm going to turn it on, but this is the most important thing I learned about it. You will get, or are likely to get, bogus readings in either ESR or DCR modes if you do not have the test lead shorted when you go into those modes. There is a function here on the button to zero it, and that also requires that the leads be shorted before you push the button. So the only time that I can see that it consistently prompts you to short the leads, waits for you to short them, and then does a zeroing is when you first turn it on and you go into ESR mode, because that's the default mode. In that case, it will prompt you to short the leads together, and I will demonstrate that. But after you've done that, the best practice that I found is short the leads whenever you're going to change anything. If you're going to change from the alligator clips, which I talked about before but I didn't demonstrate it, you've got the banana plugs on the test leads, which comes from the test cable, and you can plug in the probe or you can plug in the alligator clips. I've found so far that the alligator clips are the more useful because most of my testing is out of circuit. So I'm going to turn it on and let it prompt me for the initial shorting. So I push the button, tells me about itself, tells me their website, which I don't think works, and it says short the probe, needs to do probe compensation. So I just go over here and hold the tips together for a couple seconds, and I didn't do that well enough. It is a little tricky to do this with one hand. Now I've done it and the meter goes to its normal display for ESR. And the probes are open, so it says probe open or ESR is greater than 20 ohms. The rest of the display, when it's not saying that, will tell you that it's in ESR mode, but of course it tells you that here anyway because it mentions that the ESR is greater than 25 ohms. There will always be something on the display saying either DCR or ESR. Sometimes it'll say it twice. So let's check the ESR of several capacitors that I've already checked, just things from my parts bin. These are all new unused parts, and I've used another meter that I have that can measure DCR and ESR, and because this meter tests ESR at 100 kilohertz only, non-selectable, when I did the ESR tests on these capacitors, I set the other meter to 100 kilohertz as well. Now 100 kilohertz is a sort of industry standard frequency for testing ESR of capacitors that you're going to use in a switching power supply, high frequency applications like that. Normally you'd use something closer to 1 kilohertz for testing of the capacitors if you're going to have them in a, power supply that's a linear power supply. It's dealing with something below 100 hertz. And most ESR testers can be selected between multiple frequencies, at the very least 1 kilohertz and sometimes 10 kilohertz or even up to 100 kilohertz. This meter is only 100 kilohertz, so you have to bear that in mind. The readings will be a little different. In general, I found that the higher the test frequency, the lower the ESR value. So just bear that in mind. So I'm going to start out with a 1 microfarad capacitor. Now you do have to discharge the capacitor before connecting it to the meter. So you always want to short the leads out, even if you think there's no charge on it. You don't want to damage the thing. It does supposedly have some input over voltage protection, but even though it says that, it says also in the fragmentary instructions I found that yes, you should short the cap before you connect it, regardless of any other consideration. And it does remind you here. So, let me short out this cap. I've been doing it just with my aluminum handled X-Acto knife, holding the leads across it for a second. I also want to point out that when you're testing ESR, it's applying an AC waveform, not just a pulsating waveform, but an actual AC waveform that reverses polarity, goes above and below 0 volts when it's doing it. And therefore it doesn't matter what the polarity is on the test leads. Red and black can go to either end of the capacitor if it's a polarized capacitor. And that also reminds me that I found some information that says that this is really only designed to be used on electrolytic capacitors. You could use it on other capacitors, but the range of capacitance that it's designed to work with is 1 microfarad and higher. And you don't see a whole lot of non-electrolytic capacitors that are 1 microfarad and higher. They're mostly much smaller, 0.1 microfarads, or much smaller than that. So if you want to test ESR or DCR on smaller capacitors, this may not be the best tool for you. However, it might still work, especially for the DCR. Anyway, getting on with the test. So I'm going to connect this up now. Okay. And it's reading ESR of 0.77 ohms. The value I got for this capacitor using the other meter at 100 kilohertz was 1.8 ohms. So there's a disparity there. If it was testing, for example, at 10 kilohertz, it would have been 2. So I'm getting inconsistent results here. Now with the 220 microfarad cap, it's showing that it's open. Why is it doing that? Is it not making good connection? Something is fishy here. Maybe we should re-zero it. So I'm going to connect the test leads to the same side of the capacitor, and I'm going to just press the button here briefly, or until it does something, and it does a re-zeroing, but it switched to DCR in the process, since this is also the button that changes between ESR and DCR. So I'm going to push it again, force it back to ECR. Okay, now I'm going to unshort the leads and connect it up to the capacitor normally. And now I'm getting a decent reading. So you always want to be cautious. If you get a bogus reading, first thing you should do is go back and re-zero the meter. So it's giving me an ESR of 0.21 ohms. On the other meter I have, it was 0.19 ohms at 100 kilohertz. So pretty close, and it was 0.22 at 1 kilohertz. So this reading is definitely in line with expectations. And you'll notice this CP value up here. This is the compensation probe, or probe compensation number. It appears to be unitless. In other words, it's not in ohms or something else. It just appears to be a number that they have used by the microcontroller that's running this meter. And it will change every time you zero it. And it can go quite high. If you have more resistance, this number will be higher. If you have lower resistance, the number will be lower. For example, I've tested this with like a 200 or 150 ohm resistor clipped in the test leads and zeroed it, and this went up to somewhere in the high 300s. But after doing that, as long as I tested capacitors, which I'd previously tested, and I'm testing them now with the 150 ohm resistor in series between the test lead and the capacitor, it was giving me the same ESR numbers, for example. So it can zero out quite a wide range of resistances. The manufacturer appears to recommend to not try to extend these probes, with, for example, extension test leads to get to another capacitor. And I can only figure they're doing that because this may not have the ability to dial it out. But my own empirical test suggests that it can dial out a fair amount of resistance as long as it's pure resistance. Now, if you use some longer test leads, then you wouldn't just have resistance, you'd have some inductance as well, and that could skew your results. So it's best not to use extensions, but it does seem to be able to dial out pure resistance. Anyway, so let's move on. I'm going to go up to the 470 microfarad cap. First I'm going to short its leads out. And notice that when there's nothing connected to the test leads, the ESR is shown as greater than 25 ohms or probe open. It does not register any resistance in any mode greater than 25 ohms. It only goes up to 25 ohms. So if you see that in ESR mode, you know something is wrong. You're not getting a valid reading. So let me reconnect this capacitor. Okay, it's giving me an ESR of 0.15 ohms. On my other meter, it gave me 0.17 ohms at 100 kilohertz and 0.2 ohms at 1 kilohertz. So the ESR definitely changes with frequency, although on probably most capacitors it won't change dramatically. But the reading here is certainly a reasonable one in line with what my other meter says. And now I've got a capacitor made out of two 1000 microfarad capacitors in parallel, so 2000 microfarads. And I'm getting a ESR of 0.05 ohms. Now the equivalent series resistance of each of these caps is going to be higher, but because they're in parallel, it results in it being lower here. So 0.05 ohms. What did my other meter say? 0.05 ohms at 100 kilohertz. So I would say that in general this meter is pretty reliable in terms of its ESR readings. It matches pretty closely, for the most part, some small exceptions, but pretty closely to what my other meter says. And so I'm pretty happy with that. You just always have to keep in mind that the ESR values you get with this are likely to be lower than you would get if you were testing the capacitors for something like a linear power supply or an audio circuit where you're working with audio frequencies, because the ESR values are lower with higher frequencies and higher with lower frequencies. Again, not always a dramatic difference. It depends on the capacitor. With my other meter, I was seeing very small differences in ESR with large capacitors, and more significant differences in ESR with smaller capacitors. And that is correct. That's the way it works. Although you can probably always find exceptions to it. There's a wide variety of capacitor types and conditions out there. But you know, if you really want to get the most accurate result at applications that are not like switching power supply type applications, where you're working at higher frequencies, this may not be the product for you because you can only test at 100 kilohertz. But again, for most capacitors the difference isn't that great, and you can easily get a go no go kind of thing. So I'm going to go back and cycle through these capacitors again and check something slightly different. So now that I've demonstrated that, let me connect up the same capacitors again. And obviously it's much easier to do this two-handed than one-handed. Okay, I may have had a dodgy connection when I connected this capacitor first, because this time when I've connected it, it's giving me an ESR of 1.84 ohms. And when I tested it with the other meter at 100 kilohertz, it was 1.8 ohms. So really close this time. The value I had before may have been skewed by not having a real good connection with the clips on here. Okay, so how do we interpret this normally? There's a chart on the front of the meter, and you have to consider both the capacitance and the rated voltage of the capacitor when you're interpreting the ESR values. So I know this is a 1 microfarad capacitor rated for 50 volts. So I go to the 1 microfarad line and go down to, well, there's 63 volts. That's the closest, and it says 6 ohm ESR is considered good. And we remember that with ESR, the lower the ESR number, the better it is. A higher ESR number is bad. So it's saying here
that a typical, these are based on empirical tests, probably measuring a lot of capacitors and averaging them to get these typical values. But they're saying here that an ESR is of up to 6 ohms is acceptable for 1 microfarad 63 ohm or 63 volt capacitor, and this one tests at 1.8 ohms. So this is a very good capacitor in regards to its ESR. With the 220 microfarad cap, and I'll find 220 microfarads here, and it's a 50 ohm capacitor, so once again I'll go down to here, and it's saying that a typical ESR value is 0.25 ohms, and it's 0.19 ohms here. Since low ESR is better, this capacitor here is reading better than typical. Moving up to my 470 microfarad cap again. 470 microfarads, and this is a 25 volt part, so I'll go down to here to the 25 volt row, and it's saying 0.25 ohms is typical, and I'm getting 0.17. So again, this capacitor tests better than typical. And then finally for the 2000 microfarad cap, it jumps here on the table from 4700 microfarads up to 10K, so I'm going to have to interpolate between 470 and 1000. I'm just going to go with 1000. It's closer than 4700, and it's also a 25 volt part, so let's go down here to the 25 volt row, and it's 0.10 ohms, and I'm getting 0.04. Now that again is better than if I was just testing a regular 2000 microfarad cap, because this one is built out of two 1000 microfarad parts. The ESRs are in parallel and thereby lowered, sort of, not artificially, but more than you would probably see if I just had one of these capacitors and it was a 2000 microfarad part. So a very good ESR reading for a capacitor of this size and voltage. Okay, let's switch to DCR, and once again, even though the instructions don't exactly say, they just say you have to do probe compensation when changing modes or changing from the alligator clips to the test probes or back. So I'm just going to clip these together like this. You could also hold them together, but since I'm doing this one-handed, I get better results with them actually clipped together. I'm going to push the button here to go to DCR mode, and it's going to do a zeroing, and now it shows that it is in DCR mode, and the probe compensation is still about what it was for ESR, so I haven't really changed the test leads, so the CP number should be similar. And it's showing that I've got 0 ohm now, which is what you'd expect because it's shorted out. If I open up the test leads, now it's going to say that the DCR is greater than 25 ohms because it's essentially infinity at this point. Now with DCR, a higher number is good. You want it to be infinity if you can arrange to have that, because what the DCR is it's telling you the resistance between the leads of the capacitor. And a capacitor at DC, not AC, but a capacitor with a DC signal on it should have, not infinite, but a really high resistance. If you start getting a lower resistance, that's indicative of a failure of the internal structure of the capacitor. Now, of course, if you're testing at AC, then you get capacitive reactance, and the apparent resistance in the form of reactance changes with frequency and could be, all over the place depending on the size of the capacitor and the frequency. But since we're testing DCR, DCR means DC resistance, we're only going to test the internal resistance of the part with a DC voltage on it. And again, it should be pretty high. So I verified that the meter thinks it's infinity, and you should always double check by shorting the probes together again and watching the display. It should go to, 0 or really close to 0. If it does not do that, then do not proceed with the DCR test because it'll be invalid. I found in my experiments that I would do the short the probes, open the probes every time before I measure another capacitor and make sure it goes between 0 or really close to 0 and DCR greater than 25 ohms. So I'm going to connect this up, and now because it's a DC voltage, we do have to observe probe polarity. And it's showing this part is, greater than 25 ohms. And 25 ohms or 30 ohms, depending. Some meters use 25 ohms as the threshold. Some use 30 ohms as the threshold. And anything in that ballpark is considered the rule of thumb for good DCR versus bad DCR. So as long as the DCR is less than 25 ohms, it's considered a bad capacitor. The resistance is too low, indicates some sort of breakdown or failure, or just an outright short circuit of the internal structure of the capacitor, and that capacitor is dead. If it's over 25 ohms, it's considered good. So this capacitor is testing good. And I want to point out something that's really important. With DSR and ESR tests, or DCR and ESR tests, if you just test ESR and do not test DCR, the ESR value may be looking good. But then you could say, well, it's a good capacitor. Then you do a DCR test and it shows it's shorted or nearly shorted, and that's a failed cap. So even if the ESR number looks fine on a capacitor, if the DCR shows a low resistance, you got to throw that part away. Because if it's not a direct short inside the capacitor, but it still has a low resistance, it can still hold a charge, even though it doesn't hold it very well, and it'll probably self-dissipate pretty quickly because of that resistance. But when you're testing it at 100 kilohertz, you'll still see that the capacitor behaves as a capacitor to some degree, and it may give you an ESR number that still looks okay, if not great, and you'll say, good part. But then you do the DCR and you find out it's actually a part that's gone bad inside. So you always want to check both things. So let's move on to another capacitor. Let's try this little guy here. Once again, I have to observe the polarity because it's a DC voltage I'm applying in DCR mode. And once again, it shows it's good. But if I double check myself and short the leads together, and I can do that here by just clipping both test clips onto one lead of the capacitor, make sure it goes back to 0. Repeat the test maybe, and make sure it goes to greater than 25 ohms. So I won't show you all the other ones because they're going to have similar results, but that's the way you test DCR. What about in-circuit capacitor testing? Well, I've got some capacitors here on this board, the vintage electronics board from the 70s, and I'm going to do some in-circuit testing. I could use the probes and probe from the back of the circuit board, which is kind of touchy because this board has some sort of a lacquer on it or something, I don't know what. But when I tried this experimentally before shooting this video, I could not get a good bite through with the probes, and I had to use both hands to really push them hard down on the copper to get proper readings. I can't demonstrate that here with one hand holding the camera, so I'm going to clip directly onto the capacitor. Now these are two capacitors of 2,000 microfarads each, and they are paralleled on the circuit board. So it's really a 4,000 microfarad. So I'm going to collect, oh, I got to short this out first, got to do that. Alright, so I've got the test leads clipped onto the paralleled capacitors, and it's giving me a DCR of greater than 25 ohms. So that's good, but is it really good, or is it lying to me? So I'm going to go over here and clip on to the lead of the other capacitor, which I know is electrically common, and it does reflect that the DCR is 0 now, so that was a good DCR test. Let's try this other capacitor. It's really hard to get onto this one with these big test clips. Okay, and it's showing that it's greater than 25 ohms, so that's good. Now let's short the test leads together. And I'm going to put the meter back into ESR mode. Let it do its zeroing thing, and now we're back in ESR mode, showing 0 ohms. Test leads are shorted. And now it's showing probe open with the test leads unshorted. And I'm connecting up to the large capacitor. And it's showing an ESR of 0.02 ohms. So let's see. This is a 4,000 microfarad capacitor, so I'm going to use the 4700 as the closest. And it's 15 volts, so I'm going to use the 16 volt row. 0.06 ohms would be a typical value, and this is 0.05 ohms. So that's confidence inspiring there, isn't it? Let's try the other guy. Okay, ESR 0.25 ohms. This is a 100 microfarad 70 volt. So we'll go to 100 microfarads, go down to 63 volts, and it's saying 0.5 would be considered acceptable. This is 0.25, so it's lower, and that means it's even better. So both of these capacitors, all three of them, are working just fine. Don't need to change them. Actually, still I'm going to change them anyway, just because when I work on vintage electronics for my collection, I just replace all power supply electrolytics just as a matter of course. Now this is a non-electrolytic capacitor, and it appears to be 8 microfarads at 200 volts. I wonder what I'll get if I try testing this. Okay, it's measuring 0.02 ohms, and I'll see if the display changes when I unclip the meter from the part. It does go to open. Reconnect it. 0.02 ohms. Well, let's see what the chart says. Again, it's really oriented towards electrolytics, but let's go with, what did I say it was, 8 microfarads? Let's go with 10 and go down to 250 ohms, which is, you could use 150 or 250. They're equidistant to the 200 volts it is. And it's suggesting that the ESR could be as high as 6.2 ohms. And this is reading really small. But the ESR is typically higher on electrolytics than it would be on other types of capacitor, where the ESR is usually much smaller. So it doesn't surprise me that this is such a small ESR value. So let's finally short out the capacitor here, or the test leads at least, and switch to DCR mode again. Okay, showing 0. Unclip the one side, make sure it changes to infinity. clip it on to the capacitor, and it's showing that it's essentially open. So this is also passing its DCR test. So in circuit and out of circuit, my little demonstration here has shown how this works and the precautions you need to take to use it and how you interpret the results. I've got the clips shorted again, making sure I still get 0 there. Clips unshorted, making sure it shows probe open. And now I'm going to connect up to a resistance decade box and see what happens if I just put a resistor on here. Everything's turned down to 0, and it's showing me essentially 0 ohms DCR. DC resistance on a resistor or on the internals of a capacitor should test about the same. So I'm going to go up to 1 ohm here. 1 ohm. 2, 3, 4, 5, 6. And you'll notice something happened there. This is 5.03 ohms, 2 points of resolution in the decimals. When I go beyond 5 ohms, notice how it changes. Now it's only 1 decimal position of resolution shown. It is showing 6 ohms, which is what I've got, but the resolution changed. This meter has 2 ranges, 0 to 5 and 5 to 25 ohms. Those are the only resistance ranges it has. Everything has to be in that range. If it's greater than 25, it just says greater than 25. And of course it can go down into small fractional ohms, which my decade box doesn't do. But anyway, I did want to demonstrate how it shifted gears there from one range to the other when I went from 5 to 6 ohms. So 7, 8, 9, go back and crank this guy up to 10 ohms, and 11, 12, 13, 14, 15, 16, 17, 18, 19, go up to 20, 21, 22, 23, 24, and when I go to 25 it's actually going to be 25 point something, so it'll overrange. Well, it didn't actually, it made it up to 25.3. Now it overranged when I went beyond that. So it actually can read slightly higher than 25, but it can't read 26. So that is another function of this meter, that it can test low DC resistances just by themselves. You can use it as an ohm meter as long as you're not trying to read higher than 25 ohms. And especially in the lower ranges, you get 2 digits of resolution. Some ohm meters are less accurate than this, especially some of the cheaper ones. Little handheld, when you buy at Home Depot or something, can be pretty goofy in the low resistance ranges, and you might have one of these things just to test low resistances with more accuracy than you would get from a less expensive digital multimeter. If you happen to have to measure a lot of low resistances, it's not just my idea. The manufacturer actually does mention that this can be used as an ohm meter as long as it's a, they don't recommend using inductive resistors. You should be like regular carbon composites or metal films or something. If you use a wire wound, because it's in DCR mode, it's not going to care about the inductance. But what happens if I go to ESR mode? What happens then? So first step is I'm changing mode, so I short the leads, push the green button, go back to ESR. So now I'm testing with a 100 kilohertz signal instead of a DC signal. So frequency dependent factors start figuring in. And when I've got it down to 0 here, I'm starting to pick up some, probably a little bit of an effect from the leads. So let's go to 1 ohm, and it's got this quiescent of about 0.11 there. So 1 ohms, 2, 3, 4, 5, 6, 7. It's not as accurate as testing in DCR mode, but it still works. It's just a little further out. 10, 20, yeah. So you can still use this as an ohm meter if you happen to leave it in ESR mode by itself, but just know that it won't be as accurate as it would be if you were testing in DCR mode. One downside I've noted to this meter is that the test cable and the test clips weigh a lot more than the meter itself does. You know, if you happen to have it on a table and you know, even sitting flat on the table, and your test leads happen to fall off the bench, it can pretty much yank the meter right off the edge, potentially. It's pretty rugged, it probably wouldn't get broken, but still, you have to bear that in mind that, you know, most meters, digital multimeters and so on you've got, if you drop the test leads, it's not going to do anything with the meter sitting on your bench top. But here it can actually yank it and drop it on the floor, potentially do some damage. Okay, what else do we have? So you can force this to do a new zeroing by pushing the green button, but when you do that, it generally changes the mode as well. I have found that sometimes I can get it to re-zero without changing the mode. The manual, well, there is no manual, but the fragments of information I've been able to find online, and due to my own empirical testing, I haven't found any rhyme or reason to when it changes mode or when it does not, if I'm just trying to get it to re-zero and stay in the same mode. If somebody else knows the trick to this, you know, I tried it with a 1 second hold, a 2 second hold. You know, I'm sitting here, I'm in ESR mode. I push it down for 2 seconds, what happens? It changed the DCR mode. What if I just push it for 1 second? It stayed in DCR mode, but it did not re-zero. 1 second. It changed to ESR. I know I have caught it switching or re-zeroing without changing modes, but I don't know what I did to make that happen. Supposedly it's possible. Anyway, the worst that happens is if you do zero it because you think it needs zeroing and it changes to the other mode, you just repeat it and it'll be back in the mode you want. So what else is there? Okay, you can do a reset without turning the unit off if you just want to clear it out for some reason. Just a quick push like that restarts the microcontroller, but a longer push turns it off. I want to see what happens with a charged battery in here if I plug in the charger, what it does. Well, it keeps working. And once again, it indicates that it's charging because I have a red LED. What if I turn it off and then try to turn it back on? Well, this doesn't really mean anything. It just means that when the battery's charged, the thing will run. It doesn't tell me whether or not it'll work with the charger plugged in or not, other than that plugging in it doesn't hurt as long as the battery's also charged. So, beep, 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 short the darn thing, it says short it. So I have the test clips across a 100 ohm resistor just arbitrarily selected. I've got my oscilloscope hooked up I'm reading a square wave, not a sinusoidal wave, which I thought maybe they were approximating, but it's just a square wave. And it's about 0.7 volts peak to peak. And it's 5 divisions at 2 microseconds per division, which means it's 100 kilohertz, which is what that matches the information I found online, which they claim is an industry standard. Yeah, so not unexpected. There's a final view of the inside before I close it up. I think I'm going to try to make some abbreviated instructions for this and stick them on the back of the case. It'll probably be a good idea. Alright, I've compiled a user's manual for this ESR meter, incorporating everything I've found out or learned or empirically discovered about it. Has illustrations, gives an overview, talks about the battery and charging of the battery, how to install the battery, discharging capacitors before testing, interpreting the display, the specifications, sample application photos, a reproduction of the tester's front panel ESR chart and how to use it, whether it's important to do the DSR test before an ESR test or afterwards, etc. A caveat about the best types of capacitors to use this tester with. Talks about how to change the modes, how to re-zero the probes. Yeah. Test leads, probe clips, in-circuit and out-of-circuit testing, zeroing the tester or probe compensation, testing of low-value resistors, the 2 different ranges the tester can be in. So, 10 pages of good stuff. Tried not to be overly wordy, but at the same time I tried to use enough words to adequately explain the details to people who don't already know them. I also wrote a mini manual, which I'll be sharing along in a PDF form along with the PDF of the manual on my file share web page, which will be linked here in the video, or the link will be shown anyhow, and probably in the description if I remember to do it. Anyway, this is all the most important stuff: how to use the buttons, what the LED on the left means, what ESR and DCR are, how to measure them, what are good normal values, discharge the capacitor before connecting to the tester. Again, guidance on what's good and what's bad from the readings. Talking about zeroing again. Mentions that low value resistors less than 25 ohms maximum may be tested in DSR mode or DCR mode. Tester is best used for measuring electrolytic capacitors 1 microfarad or greater. And this is sized to be cut out and stuck on the back of the meter. Now I used some old 3M print-to-last paper, or did I use the more modern Xerox Never Tear paper? It's pretty much the same thing. I think I actually used the Xerox for this. So the toner won't come off. It's a plastic laser printable plastic film, and I use it for making all sorts of labels. Anyway, so I'm going to use my Scotch Extra Strength adhesive roller to mount it on the back of the meter case. I've applied the adhesive around the edges and down the middle, once in the narrow direction and 2 across in the long direction. And there it is. I really should have stuck it a little more to the left because there's sort of a dimpled area in the plastic that's obviously intended to have a label stuck into it, and I should have put this a little bit to the left so more of the adhesive would be on the lip of the dimple instead of on the edge of the dimple or down into the dimple, but I think it'll work anyway. It's pretty strong adhesive. I think it'll hold it down. I've also put some electrical tape on the test lead cable where the some of the jacket had been worn off, probably during an assembly mistake. The seller on eBay has suggested they're going to give me a partial refund, but they have not done so yet. It's not a critical failure, and it's not like I'm going to be using this heavily, so I think it'll be fine. But for a $40 meter, you know, it's pretty good value for the money, I think. I verified that it seems to do what it claims to do. I wish it generated a sine wave for ESR testing instead of the square wave, but it does seem to give reasonable results even with the square wave. And I would also prefer that the testing voltages were lower than they are to make sure it doesn't inadvertently turn on semiconductor junctions that might be around the capacitors under test if you're doing in-circuit testing. The manufacturer doesn't mention that. It's not in the manual that I wrote because I don't really know for sure. But I just caution in there, you know, even though you can do in-circuit testing with this meter, you have to bear in mind that under some combinations of circuitry around the capacitor in an in-circuit situation, you might get bogus results if other components start factoring into the results. One more thing I did is I put some little silicone rubber feet on the bottom so it's less slidey on the tabletop or the bench top. Stays put a lot better, less likely to slide off the table if I drop the leads. Doesn't move nearly so much.
And here's the beauty shot.